Okay, yeah, can you hear me? Okay, awesome. So today I want to talk about critiques of ML. So when I was thinking about this talk, I was thinking about what should I name it? So my motivation, I think, may have been a better title. So the alternate title I thought of was, so you studied ML and you'll soon see your relatives. Now what? So this came up in my head because about a year ago, I went home for winter break, and obviously all my relatives want to talk about what have you been doing, what have you been studying, all this stuff. And I would tell them about, I was studying a bunch of systems, all these things, and I had done just a tiny bit of machine learning. And as soon as you bring up the topic of machine learning, you get this adversarial uncle who comes into the picture. This is what mine looks like. I don't know if you guys have Tony Stark like I do as your uncle, but he instantly said something that will always stick with me, which was, so I hear they disproved AI. Like, what does that even mean? It's a whole field. How could you disprove it? And I think what he was getting at was this idea of adversarial examples, which is something so surprising that it actually made it into the mainstream. So this is something where, he's not reading archive.org. He's more on like clickbait.net or something, but he still sees that something about machine learning came out in the public, and it tells you that it's not as good as it's promised to be, and he latches onto it. So I think that once you study this field, it becomes really important to know what the critiques are and how you can counteract these critiques. And it's also important to realize that some of them are legitimate critiques. A lot of them are things that you should be worried about in your own work, things that you should defend against. And then there's also this aspect, like I'm talking about, where if your adversarial uncle tells you they disproved AI, you should be able to have an informed discussion and say, well, actually, it's more nuanced than that. Okay, so here are the topics that I want to cover. So brittleness is number one. This will be covering the topic of adversarial examples especially, which is what I think my uncle had in mind. Then interpretability, which is more than just one topic, as we'll see. I think they're doubled up. Don't know how that happened. But then data and compute expensiveness. So is this a fundamental issue that we have where everything in machine learning requires a massive amount of data and a massive amount of compute? Or are these things that you might be able to mitigate? And then finally, we'll just have a brief talk about some of the more broad community weaknesses that the machine learning community is dealing with at the moment. Okay, so on the topic of brittleness. So I think it's best to just start with the example presented in the first paper that introduced adversarial examples. So this is in the context of image classification, which in about 2013 had been making breakthrough results. And these researchers from Google and NYU came out with some very surprising examples where you could take an image, such as these three on the left, where it's been classified correctly, and then you can apply this perturbation. So here in the middle, you just see this small delta that we're going to apply to the image at each pixel. And then on the right is what happens when you subtract this from the original image. But the amazing thing is that everything on the right has been classified as an ostrich. So these are things that to a human, it's completely hidden that this has been changed. But to your classifier, it looks like an entirely different image. So this was very surprising and worrying to people. So I think it's important to first understand, well, what's really going on here? How do you compute this adversarial example? So there are a couple methods, but I think probably the easiest one to understand was introduced after this first paper, and it's called the fast gradient sign method. So the setup is you let data be your parameters as usual. X is your input. In this case, X is just a full image. Y is your target label. And then J is your cost function. So what we're going to do is create a new image, which is just the perturbed image, where we add this eta. And eta is some very small epsilon times the sign of the gradient with respect to the inputs of your cost function. So we backpropagate all the way to the input, and then you have a vector, which is your gradient, same shape as the image. And now you're going to take the sign of each component and then add some epsilon times that sign to your original image. So then putting this back into how you would visualize it, you have your input image. Your sign just looks like that. It looks pretty noisy to us, but it has some real meaning, which is related to the gradient. And then when you multiply that by epsilon, it becomes this very small perturbation. And then you add it into the image, and most of the time, you can't even tell that the image has been perturbed. Okay, so more generally, the properties of these are it's usually indistinguishable to the human eye. This is maybe the most worrying part of it. Number two, which is also really worrying, is that adversarial examples can generalize across architectures and subsets of your training set. So what this means is, let's say you put a model out into the real world, and you think that, okay, I should be safe because no one can perform the fast gradient sign method like we saw on my model. Okay, so even if they don't have access to your parameters, they can go out and train not even equivalent. They don't even have to know your architecture, but train just a neural network on the same data set, and it can even be a different subset of the training set. And then the adversarial examples that they construct can generalize to your model. So that's the other very surprising and worrying property. And then another one that's just interesting and kind of connects to the theoretical foundation of it is that the perturbations actually generalize across examples. So a lot of times, if you compute the perturbation with one image, with respect to one image, you can do that to a different image, and you can cause the same change in the output class. And then one that's made it into mainstream attention again is this idea that you can actually create physical adversarial examples. So it's not just changing an image by some small amount, but in this example, you can 3D print a turtle that, when shown to a whole array of classifiers, looks like a rifle. So this one, they're just showing you that if you arrange it in all these different angles, the turtle still looks like a rifle to the classifier. Okay, so, yeah.
Along the same example, I think there was somebody showed that you can actually print a sticker and paste it on a stop sign, and which can fool self-driving cars into thinking it's a different sign.
Yeah, I've seen that one. So Anand says there's also this other example where they printed a sticker that you can put on a stop sign, where a self-driving car would come up and look at the stop sign and say this is a speed limit sign or something totally unrelated to a stop sign, and just cause the car to blow right through it. So these are real, and as these types of algorithms make it more and more into our daily lives and things we depend upon, it actually becomes a pretty serious security vulnerability. Okay, so now we've talked about the problem, but in practice, we're not going to just throw away neural networks for image recognition, for example. It's too powerful to just sacrifice this whole tool we have. So a lot of work has gone into making defenses for these algorithms. So number one, which they introduced in the first paper that showed adversarial examples, is this natural idea of just taking your perturbed images and then generating them on the fly and then adding them into your training set and seeing, okay, maybe this will make me more robust to other perturbations that other people might think of. So this turns out to not work that well in practice. You can mix in a whole bunch of adversarial examples, and it just seems like the space is too big to find all these little pockets where adversarial examples might exist. So another technique that was proposed later on is to use this idea of model distillation, which we'll talk about later on. But essentially the idea is you train one neural network on your standard image data set with your standard labels, and then once you have this trained network, you take the outputs, which in most cases are going to be a softmax output, and then you increase the temperature, which basically just means you make the output predictions closer to uniform. And then once you have this, you train a second neural network whose objective is to match the activations of the first one. So in a sense, you could think of this as soft labels. Like you don't have 0, 1, one-hot labels, but instead you have these outputs from a different neural network that might be 0.2, 0.7, and so on, and you're trying to match those rather than the zeros and ones. So there have been a whole bunch of other defenses, but it seems that every defense that comes up, they find a new attack that circumvents the whole defense. So this paper that came out by a few of the same authors who introduced adversarial examples tried to argue that this is actually a pretty fundamental property of linear models. So any model that has linear functions built in, including neural networks, will have this property where you can find adversarial examples. And their argument is pretty simple. It's just that whenever you compute a dot product with your weight vector and then some high-dimensional input, a perturbation gets amplified by all these weights. So if you can add this eta to your input, your overall perturbation is going to be proportional to eta times your weight vector. So the higher dimensionality you have, the worse the linear model is vulnerable to these adversarial examples. So I think this has been probably proven by the fact that we just keep coming up with new attacks to these defenses that people come up with. So including this year, there have been a whole bunch of new papers on new attacks and adversarial examples. Okay, so now I'd like to switch gears a little bit to the topic of interpretability. So interpretability is a term that gets thrown around a lot in machine learning because people don't want to just relinquish all control to a machine learning model and not know what it's thinking. Like, what is this? What is the cause of your decision? Why are you telling this person they can't get a loan when we think they should? And so on. So interpretability is one big demand that comes up for machine learning models. So there's one paper that I'll talk about a little later that comes up with a bunch of desiderata for interpretability. So the first one is trust. And trust is basically the question of, are we okay relinquishing control to this algorithm? Do we trust it to make the right choice? So this is a combination of accuracy and maybe your idea of what it depends on to make its output prediction. 2 is causality. Is this model uncovering causal relationships, or is it uncovering just some correlation that we might think is actually unfair in the real world? The 3rd is transferability. So will it work on distributions that we don't really have access to at training time? So this is really related to the adversarial example case that I gave earlier, which is maybe during training time you won't have an adversary trying to add this eta to your inputs, but when you put it out in the real world, it's definitely a possibility that you'll have adversaries attacking your model. So then the 4th one is informativeness. So this is when someone's using your model, does it tell them something that they didn't already know? And then number 5 is fairness and ethics. So does this model capture something about the real world that we think is unfair? And if so, maybe we're not going to use it. Okay, so many of the ideas I'll present are from this paper called Mythos of Model Interpretability, which I highly recommend you take a look at. Okay, so this image, I think, really summarizes the main problem, which is that our objective function oftentimes just relies on a simplified version of the problem where we have an output class or some output prediction, and then we have a ground truth label. And this doesn't capture all the nuances that we have in the real world. So for instance, one that comes up a lot when you're talking about ethics is the idea of approving people for loans. So if your output is just approve or don't approve, it's hard to capture, things that someone who is actually looking at loan approval in the real world might take into account, like, is this someone who's been rejected many times? Do we think it's unfair because our training set just has a lot of people who look like this person who haven't been approved, and so on. Okay, so I'll present a couple of fallacies that hopefully you'll hear come up later after this talk, and you'll be able to say, oh, I recognize that, and I'll remember this is actually not true. So the first fallacy is if someone says linear models are interpretable, but neural networks are black boxes. So the main problem with this statement is that it doesn't fix a definition of interpretability. So interpretability can actually mean a few things. So the first category of things that interpretability can be a proxy for is transparency. So is this model an algorithm that we understand and we can simulate in our heads? And I'll cover each of these points in a little more detail later on. And then the second category is post hoc explanation. So once a prediction has been made, can I look at this and ask, what was the reason for your prediction? Okay, so the fallacy in particular is wrong because linear models actually win on algorithmic transparency. It's pretty easy for us to simulate these in our head and see, okay, if this weight is high, that means that a high value in that corresponding input means high value in the activation. But neural networks actually win when it comes to post hoc interpretation. So a lot of times, the features that your neural network learns are richer. You have access to things like seventh layer activations, things that might actually reveal more about the prediction than your linear model could. Okay, so the first subpoint, which falls under transparency, is it simulatable? So simulatable basically just means, can someone in a reasonable amount of time think through what the algorithm did? So I think most people would agree it's pretty hard to imagine an image going through a neural network. I mean, there could be millions of parameters and millions of multiplications happening, so you won't be able to simulate that. But if you think of something like linear regression with a sparse weight vector, now you can think about there are only a few multiplications going on, and you could simulate it internally. So the second one is decomposability. So decomposability essentially means, can we understand the units of this algorithm at a very low level? So in this case, you might say that actually a neural network is decomposable because I can understand what a single neuron is doing. So then the third one is just understandable algorithm. So can you understand the optimization algorithm? And this one is a little more subjective because you might say that someone who's been researching for 10 years can understand something, but most of the users will not. Okay, so under the second full bullet for interpretability is this idea of post hoc explanation. So essentially this is, you have a model, it makes some sort of prediction for you, and then after the fact you ask, okay, why did it come up with this prediction? So the first subcategory is text. So you could imagine a model where it makes prediction and then it also offers some explanation in a form of free-form sentence. So it could say something like, I saw this scan, this person has a nodule in their lung, I think they're sick. And that's pretty easy because we naturally get explanations like this from people. Okay, so the second one is visualization. So you can think of the same sort of thing, except visualize the representation that your model computes for some input. And then the third one is local explanation. So this one is particular to sequential data or images, where you might have some local structure in your input, and you could have your model produce something that shows you where in the sequence or where in the image was the most salient feature for coming up with this prediction. So a good example of this is this thing called a grad CAM. So CAM stands for Class Activation Map, and the main idea is that you have some output class that was predicted, and you want to know what was the part of your input that was most salient for coming up with this prediction. So essentially, the main idea is that you should take your gradient with respect to your prediction, and whichever activation has the highest gradient there is the one that's most responsible for increasing your class. Or alternatively, you could think, if I made this pixel look a little more dog-like, it would make its prediction more dog-ish. So these are what they look like in practice. The bottom row shows you if the class is dog. You can just see like the heat map comes out on the dog's face. And then similarly for the cat, comes out on the cat. So these can be useful, but we'll also see later on they can also be pretty misleading. Okay, and then the final subpoint is explanation by example. So this one might be more useful when you have a large training set that you understand very well. So the idea is you should take some test prediction and then ask your model what was the most similar training example that you saw compared to this one. So the idea might be you compute activations for your test input, and then you do something like k-nearest neighbors to all your activations on your training examples, and then you just see which one was closest, and you report those as an explanation. Okay, so fallacy number 2 that I'd like you to remember is if someone says all AI applications must be transparent, you should think, well, it really depends on the domain. I mean, if you're very certain that you need to know exactly which feature was important for making a prediction, sure. But the reason that we shouldn't take this as an axiom is because there are a whole bunch of examples in the real world of things that surpass what we could handle in terms of complexity, but actually make our lives a lot better. So for instance, airplanes. Is this a transparent algorithm? I don't think the vast majority of people who fly in airplanes understand the intricacies of how an airplane engine works or even know how to fly one. So if not, why do you use it? And I think the answer is because it adds so much value to our life that is worth it for the risk that we take that just not understanding this algorithm might make it dangerous to use. And we also have had a long history of thinking about the risks of airplanes. I mean, we have a track record of at least 40 years of people flying on airplanes and being pretty safe. Okay, so to kind of formalize what I've been saying, full transparency can preclude models that surpass our ability in complex tasks. So if it has to be transparent to the point where a person understands every detail, then it kind of makes it impossible to surpass what you could do on that same task. Okay, so fallacy number 3, I think this one's the most obvious of the 3, is always trust post hoc explanation. So there are a lot of cases where you can train an algorithm and optimize hyperparameters so that your algorithm comes up with good post hoc explanations. So for instance, if you always look at the class activation maps while you're training an image recognition algorithm and you see most of them were bad, but I found this one that actually gives pretty good in the sense that it looks like what I would look at to classify this image. So they can be optimized to mislead you in the same way that people can optimize what they say to mislead you about the decisions that they made. So there's a whole bunch of examples of this in social science literature, like in college admissions, people saying things like, oh, this person has good leadership or this person has good originality, but when you actually look at the cause of their decision, it is pretty clear that it was made by other things like gender and race. Okay, so to summarize all this, don't discuss interpretability without first fixing a definition. So you should either talk about transparency or post hoc explanation and then hone in on those definitions to decide whether or not what you're doing is interpretable. Then be aware of these interpretability fallacies. They get thrown around a lot, and you should at least understand that they're not so black and white. Then find a domain-specific definition of interpretability that fits your domain and use that one. And finally, I think at a higher level, we should think about how to solve this core problem, which is don't optimize for something that is not actually the task that you want to accomplish. So for instance, don't just optimize for class labels if you really care about localizing something in an image. You should instead treat it as a localization problem and have labels and optimization functions that are actually localizing. Like for instance, just treat it as segmentation. Okay, so to shift gears, again, another topic that comes up a lot in critiques of ML is this idea of expense in terms of data and computation. So I think data is probably the one that is harder to deal with. So we'll cover that one first. So data is expensive in terms of the collection and also in terms of computation. And it's expensive in the sense that it takes a long time and it oftentimes costs a lot of money to collect these things. So the first category of solutions to this is to use unsupervised or unsupervised pre-training algorithms. And then also you can use semi-supervised approaches. So one thing that took a surprisingly long time for me to be introduced to was this idea of unsupervised pre-training. So the idea is even if you have a supervised learning task downstream, you can use unsupervised pre-training to initialize your algorithm and in a lot of cases get performance that wouldn't be possible in a strictly supervised setting. So here's a diagram that roughly gives one approach, which is that you should do layer-wise pre-training with some sort of unsupervised algorithm. So usually this is something like an autoencoder where your goal is to have some compressed encoding and then also come back and reconstruct the image or reconstruct whatever input you have. And you do this layer by layer at each step, reperforming your optimization. So a newer technique that is maybe a little more intuitive for people is this idea of data distillation, which is just expanding your training set using the algorithms that you've already trained with supervised approach. So the general idea is to take multiple transformations of an input that doesn't have a label and then combine these predictions into a new label, and it may or may not be correct, but you can still use it in training, and it actually increases your performance. So I guess the general idea would be you could use all Google search images, say if you're doing image classification again, and you could just take hundreds of thousands of images and do multiple crops and multiple small distortions, and then average your predictions, and you could get new labels for your training set. Okay, so probably the most commonly used approach to deal with the cost of collecting data for your specific task is to use transfer learning. So the main idea is that you should pre-train whatever model you're using on related tasks. So the closer, the better is the general rule of thumb. So let's say, for instance, using image classification again, you're trying to do something medically related, so you have medical images, but you don't have hundreds of thousands or millions of these. Let's say you only have a dozen. Then it would probably help you a lot to pre-train on a public data set like ImageNet. Or even better, you can just download model parameters. So a lot of times people publish parameters, especially for neural networks, is very popular, and you can just download these large files, and then you just load them from memory and you run your algorithm. So this is recent work from a group at Stanford, and their work they call taskonomy, which is supposed to be a taxonomy of tasks. And the idea is to just show you that there are relationships between tasks where some are more closely related in the sense that pre-training on one will help you most on another. So if you take a disciplined approach to this, you can make your pre-training pretty efficient, and you can end up helping tasks that you thought were unrelated, but through this taskonomy were actually pretty close. Okay, so now shifting from data to computational expense. The first issue with computation might be large memory constraints. So, for instance, if you have a model that has 100,000 parameters, it might be difficult to fit this onto a specialized accelerator like a GPU that has a really highly constrained memory. So the first idea is to use compression techniques. So, and this kind of goes along with the idea of using quantization. So compression, I'm sure a lot of you are familiar with, is essentially reducing redundancy in data through a lot of information, through a lot of algorithms that are used in information processing and signal processing. And then quantization is this idea of taking things that might be considered approximations to continuous values, like a floating point number, and then quantizing it to something like binary zeros and ones or ternary or a little larger. So yeah, the general question is why use float 32 for all your weights when you could use something like 0 and 1? Okay, and then the third category is a little more extreme, which is to actually start from the hardware and reinvent this problem. So once we've arrived at these new algorithms, it's been clear that a lot of the hardware that's been designed prior to the development of these algorithms is not actually optimal for this task, and you end up spinning your wheels a lot of the time, doing things that wouldn't need to be done if you had more specialized hardware. So GPUs in particular are something that's probably going to get replaced with other more specialized tasks, more specialized hardware, and things like FPGA, which stands for Field Programmable Gate Array, and TPU, which stands for Tensor Processing Unit, will replace GPUs just as a more efficient way to perform these large matrix multiplications and so on. Okay, so this figure below is taken from a work that pioneered a lot of this field of compression and quantization for neural networks, and this is called deep compression. So the general idea is to use this 3-stage approach after you've trained your network, which is to first you prune your network, which means you go through and essentially find weights that are redundant. So you find things that if you remove them, the same computation would still happen, just say elsewhere in the layer or maybe at a later layer. And then the second step is quantization. So again, this is the idea of taking these weights that might be represented as floating point numbers and then binning them into something smaller, for instance, maybe an 8-bit number, so you have 256 values, or you could go even smaller in a lot of cases. And then the third one is to apply Huffman encoding, which is just a compression algorithm. And once you do all of these, you end up with 50 times gains in a lot of cases. So this essentially means you had a model that required 50 million parameters, and after the fact, you have 1 million parameters. And along with that, you also, it's not just memory savings, but the number of floating point operations, or in this case, binary operations, goes down by the same factor. Okay, so aside from doing this post-training compression and quantization and things like that, there's this other fork of the attack, which is to actually design efficient models from the beginning. So in many cases, this might just mean taking a step back and thinking to yourself, do I need to use this complex, fancy neural network application, or maybe I could use something simpler, or at least try a baseline. So once you, let's say you have settled on the fact that you do need a neural network or something similarly computationally expensive, then you should take a look at the research, because a lot has been done in terms of trying to question every design decision that's been made to arrive at state-of-the-art neural networks, and then peel them away and figure out which ones are actually necessary until you arrive at the most efficient but still performant network. So similar gains to deep compression have been found just through changing the setup for each layer of a neural network. So a second idea is to use this thing called knowledge distillation. So this has come up twice now, and I think it's time to actually explain it. So knowledge distillation came up in the context of training an ensemble of models, which means you train 3 or 4 models on separate splits of training data, or perhaps train them just with different random initializations, or even different algorithms. And then at the end, you want to compress this down to one single model. So the general idea, again, is that we're going to take all of the outputs of your ensemble models, and you'll just save these with an increased softmax temperature. So this means if they were predicting things like 0.8 and 0.2, we increase the temperature and make them a little closer to 0.5 or whatever the uniform value would be. And then you save all of these, and you just replace all your labels with these softmax predictions. And then in the end, you just retrain a single model that gives you basically all of the gains you had from your ensemble, but it's much more efficient, because instead of in a forward pass running 4 or 5 models, you just run a single one. Okay, so to summarize approaches for reducing the expense. One is data. So transfer learning and public data sets are probably the most popular approaches. And again, this means either downloading weights or pre-training yourself on public data sets. And then unsupervised pre-training probably comes after that, followed by newer techniques like data distillation or other things that come out frequently, but probably require a little more scrutiny on your behalf. So then to tackle the idea of how expensive it is to actually compute a lot of these models, compression is one thing that has come up a lot recently. Quantization is another very hot topic. And then third, specialized hardware is probably going to become more and more relevant. Okay, so the final topic of critiques of ML, like to talk something about a little more technical, a little less technical, but still probably comes up just as often in mainstream view of the machine learning world. So this is the idea that the community has certain weaknesses that have one way or another seeped in and probably should be addressed explicitly. So the first one is the cycle of hype and winter. So a lot of people who are new to machine learning might not know that prior to the 2000s, there were actually multiple AI winters. So these are times where funding and interest in AI and machine learning has basically gone down the drain. So there was a peak, I think, in the mid-70s of interest in AI, and then a few researchers published a large critique of machine learning, which seemed to say that most of the promises that had been made in the 70s were never going to be realized, and funding dried up within a couple years. And then a similar thing happened in the European community, and it was really detrimental to research. So I think the cause of this is really overselling things that before you know what their true promise is. And then the other thing is just knowing that these things will come. So knowing that probably people will pull back funding or people will lose interest in the community, but you should stay strong. Okay, so the second thing that comes up is lack of rigor and lack of tight scientific method in the machine learning scholarship. So there have been a few papers that lay out just general trends in machine learning, and these include things like publishing something where you say there were 5 or 6 algorithmic changes that you made, but then not reporting which ones actually helped performance. So the general term for this is an ablation study. When you have 5 or 6 changes that you make and performance improves, you should narrow down which exact changes were responsible for creating that performance boost. So the result of this is that people will end up inventing theories that turn out to be incorrect to explain observed performance gains. So a recent example of this was on the topic of batch normalization. So batch normalization was a method introduced to make it easier to train deep neural networks and make them more stable. And the explanation that was originally presented in the paper was this thing called internal covariate shift. And so this was generally accepted, although no one really understood it. People accepted that this is what was happening, and the performance gains were so good that people just moved on and used it. But recently, people have come back to the algorithm and asked themselves, well, is this really what's happening? And in many ways, they've shown that it's probably not what's happening. There's probably something different going on. So this just goes to show that if you don't investigate what happens, other people will do it for you, and it should be pretty embarrassing. So this talk, cited as number 33, is definitely worth giving it a watch. But the general suggestion of the talk is that when you see something that happens that you don't expect, you should spend more time finding the root cause of that result than just trying to chase the performance gains that it might have produced. Okay, so another topic that comes up in the machine learning community is the lack of equal representation. So in terms of just who the machine learning community attracts, it tends to be male-dominated and also dominated by a lot of different races that don't reflect the cross-section of the United States and of places around the world. So there are efforts to counteract this. There are groups that explicitly try and support people of underrepresented ethnic backgrounds, and those are cited there. So then there's also these large barriers to entry. So this kind of relates to expense through data and compute, but it also relates to that there are only certain universities in the world that provide a well-rounded education in machine learning. So it's such a new field that it's difficult to gain entry, or it has been historically. And there are things like massive online courses, which Professor Eng has spearheaded for a large portion of it. And these should help to make it more accessible to the rest of the world. Okay, so just to summarize the points we covered. So brittleness, this was adversarial examples, and asking ourselves, is this a fundamental issue with models that we've been using? Then the second topic is interpretability. So there are multiple definitions of interpretability. You should ask yourself, which one do you care about for your domain, and how can you make your models more interpretable in that sense? Then the third topic is expense. So how can you reduce the data intensiveness and the computational intensiveness of your applications? And then finally, we touched on community weaknesses. So these are things you should watch out for, and make sure you don't perpetuate the weaknesses that have come up. So I'll leave you with this last quote, which is from Jeff Hinton quoting another great scientist. And he says, Max Planck said that science progresses one funeral at a time. The future depends on some graduate student who's deeply suspicious of everything I have said. So his general message is, you shouldn't just accept what researchers before you have come up with, but you should question the reasons for what they found, and you yourself should explore entirely new methods that might fix the issues that we've seen. Okay, so that's all I have. If people have questions, I'd love to talk about your critiques as well. Yeah.
Going back to your slide about the plane analogy.
Yeah.
The black box is like a plane. I don't know if that's necessarily like a true analogy, because yes, it is a black box to the average person, but there is an engineer at Boeing who knows every single component, why they have that component. Whereas in the case of like neural networks, we still don't know why we have these number of layers in our model, or why we can't, why is it fully connected? Like, what is the reason behind all that?
Yeah, this is true. So the question is, or the comment is, maybe the plane analogy isn't so good, because although the average user doesn't understand it perfectly, there are engineers who understand the components. So I think you bring up a good point. In a way, it's definitely not a perfect analogy. But I would argue that there are certain parts so the whole airplane as a system, I would actually argue that no single engineer understands every component. That they have to have interfaces that simplify the components, put them together in a way to make the whole system work as a whole. And I think for neural networks, there may be, I guess you could argue there are some components that people don't totally understand. But I would argue that it's similar in that there are some components that no user would ever understand, but some engineer somewhere understands why this works. But also maybe there's other analogies in the real world, not like airplanes, but in the aerospace world, like rockets that go at Mach 7 or things where the fluid dynamics change entirely, where they don't understand, but we still use them because in practice they work. So yeah, I think that's a good point. Just should be careful not to make this analogy, but I still think the general idea is true that if we require full transparency in the purest sense, then we can't really surpass our own performance on every task.
I think related to the same point, I agree that the airplane analogy might not be the best analogy, but the point still holds, because there are other examples such as, in medicine, there are lots of commonly prescribed drugs like aspirin, which, nobody actually knows how it works, at the molecular level, but, it's FDA approved, doctors prescribe it, and it's widely used, but, if somebody asks, any doctor, how does this actually work, I don't think anybody knows, but we start with it.
Yeah, so just for the video, Anand brought up the other example of in medicine, there are drugs like aspirin that people prescribe where actually we don't understand at a molecular level what's going on. But because it's so effective and it saves people's lives, we'll still prescribe it. So we don't shy away from it because the benefits are actually enough to counteract our lack of understanding. Okay, cool. I think that's it for today. Thank you all for coming. Appreciate it.